All right, 7.4, vectors and the dot product. So we're going to start using a lot of our trig concepts, solving triangles, non-right triangles, angles, all those fun things we've been learning throughout the course here. And we're going to start applying those to vectors and vector situations. So to start with, we got just some basic terminology. One of the things we need to understand is that there's a lot of different terms that are associated with vectors, so we got to understand what they mean. One of the first things that always comes up is something called a scalar. And scalars are quantities that involve only a magnitude. You're pretty common, or these are pretty common things. You guys work with these a lot in the real world. When you're driving your car, you're going 60 miles an hour. Okay, that's going to be considered a scalar. You grab a bag of potatoes that weighs 15 pounds. Okay, so those are things that there's only an amount, there's a weight, there's a measurement of some kind. But what it doesn't tell you is, 60 miles an hour down the highway doesn't tell you what direction you're heading or which direction this force, which is another kind of key word that comes up with vectors, which direction that force is being applied. So scalars is just kind of the amount. The magnitude is the word we use in vectors generally, and the magnitude is represented by the length of a vector. It's kind of its amount of force or its strengths that's being applied to a point or an object or something along those lines. Um, to come up with a true vector, we need to know direction also. So we're going to be given both a direction and a magnitude, and that's what we generally refer to as a vector quantity or vector quantities. It involves both. So it's not only going to tell us we're traveling 60 miles an hour, but which direction we're heading, north or south or east or west. So we have both a force and then also a direction involved with these vector quantities. The next one is just a vector, and that's just going to be what we call kind of a directed line segment. Okay, kind of the notation for vectors is a lot of times you'll see them with two letters, like vector OP here with a little directed line segment above it. These are rays, so there is a kind of an ending point, or what we call probably a starting point, initial point, and then it heads off to point P, but doesn't stop there, it just keeps going. That force is being applied infinitely in that direction. In our book, a lot of times vectors are represented with just capital letters and bolded. Okay, it's tough to put these little symbols in the book sometimes, so it's a lot easier to write just some bold letters. But each one is going to have some point where it starts, which we call the initial point. So this one is in the order in which these things are written is important. So vector OP would have an initial point, or starts at OP, and again, that's also the point of which the force is being applied. So if there was an object there and we were pulling it off into direction P, well, that's what we call the terminal point. Very similar to the things we've talked about with our angles and standard position and all that stuff back from earlier chapters. Okay, the terminal point kind of allows us to determine the direction. So it starts here at O, goes through point P, and from that, because we know where it starts and which direction it heads to or which point it heads towards, we are able to come up with the direction, and then the length of that vector can be represented or represents its magnitude. There's one other thing we want to take a quick look at, and that's something called an equal vector. Equal vectors, in order to be considered equal, two vectors have to have both the same magnitude, so they got to be the same length, and also being forced upon or applied in the exact same direction. So here's two examples of what we would call equal vectors. Vector N, vector W. We can also use just a single letter to represent the notation involved with vectors. But a single letter, they're both pointed in that exact same direction, kind of up and to the left there. And then they are of the same length. So those two vectors are what we consider equal. And a lot of the things that come up with vectors is going to be determined not necessarily equal, but maybe opposites. Okay, what forces do we need to apply to a certain vector to get it to cancel out or become or cancel it out essentially. Okay, here we go. Now we're going to move on. We're going to take a look at kind of a visual depiction of um, how these vectors are going to play out and how these forces kind of combine to act together on a single point or a single object. So what we're going to look at doing here is finding the sum of two vectors. There's kind of two methods that are used, and both kind of have their benefits. We'll look at both of them. You'll kind of use the one or both at certain different times that you prefer. The first method we'll look at is finding the sum of two vectors using this tail to tip method. And we're basically going to set up a triangle here, but the sum of two vectors is just going to be um, the, basically what we call the resultant of vectors A and B. And kind of the setup here would be something along the lines of, hey, two forces are acting on a point. This point right here on a plane, vector A has this magnitude, and again, that's represented by its length, and it's pulling in that direction. B has this magnitude, a little bit less of a force, but pulling off in this direction. If there is a rock there or somebody in a sled with two handles, which direction and with how much force would that slide or rock be being pulled? So if we want to find vector A plus B, what we'll do is, and the order is semi-important here, but we'll start with vector A. Okay, so here's vector A. And what we'll do is we'll move vector B to the tip of vector A. So here's where they started. What we're going to do is just slide B to the very tip of A, and then we draw in this new vector. And this new vector is what we would consider then the sum of A and B. So with those two forces acting on that plane, this would be vector A plus B. Okay. And you can see right there, we went ahead, we set up a few, or basically a triangle. So if we knew the sum of vectors A, or the magnitude of A, the magnitude of B, and maybe the angle that was formed between them, okay, we could probably go ahead and solve for AB, which will allow us then to, answer the question which direction and with how much force would be acted upon that one point there. All right, so let's take a look at the parallelogram method next. And basically the parallelogram method is just going to be the tail to tip method twice. And again, we used that word in the last one. We didn't call it that last time. But this one will say find the resultant of vectors C and D. And that is, again, just their sum. So what we do is C is listed first, so I always start with that one. And then we're going to go tail to tip two times here. So take vector C there. I'm going to go the tail to tip method. So I'll put D on the tip of C. And then we're also going to put D and C, just kind of how they interacted normally. That's what's nice to see about the parallelogram method. But then I'll also move C to the tip of D, and we should form a perfect little parallelogram. And like I said, both methods are important. We do want to know how to use both, because at certain times we get a little more information with one than the other. And again, then the resultant here, or vector C plus D, would be the diagonal that is formed between those two. So this vector here is what we call vector C plus vector D. And that is also, again, called the resultant of those two vectors. So you can kind of get an idea, if this force here is pulling horizontally or flat in that direction, this one's pulling off in that direction, we would assume that, hey, it's going to be a little closer to C because, it's got a little more magnitude, but D is going to have an effect. And you can see that the forces being applied, even though they're not being applied in the same direction, still, increase the force that's being applied on that original point. So here we go. Take a look at the next one. So those are our two methods for sums, tail to tip, parallelogram. Now we've got to talk about what an opposite vector is. And for every vector, there is another vector that's considered its opposite. And all you need to remember there is that they have the same magnitude, but they face the opposite direction. So if here's vector V, okay, we could easily figure out what the opposite of vector V is by just taking that vector, and again, it needs to be pointed in the exact opposite direction. So I'm going to clone that thing, and I'm going to flip it so it's opposite direction. It should still be the same length, but it'd be pointed exactly opposite direction. And if that's the case, we usually call this negative vector V. And kind of the key important feature here would be, we can probably guess what angle is formed between those two. It actually forms a straight angle. There'd be 180 degrees with opposite vectors, you always kind of want to ask the next question, what happens if you would add vectors v and negative v? Okay? And if you did that, you can see that the sum of this vector, if you go tail to tip, either one way or the other, you're going to see you get a vector that just looks like this, okay? A dot. And that's something that we call the zero vector. It has a magnitude of 0, so there's actually zero force. These two vectors cancel each other out completely, and the direction is what we would consider arbitrary. Or in other words, it doesn't really have one. It could be facing any direction, but if you're not applying a force, it doesn't really matter which direction that it is being applied. All right, one last thing here, subtracting vectors. Okay, well, we really don't ever subtract the vectors, but instead we just add the negative. So if we're trying to look for vector a minus b, we're really just going to go ahead and find whatever a plus the opposite of b is. So here, if we take a look at this one real quick, find vector a minus b. Here's a, here's b. What we're going to want to find is obviously the opposite of vector b. So this right here, if we can grab one of those, flip it around so that it's facing 180 degrees in the opposite direction, but again, the opposite vector would have the same magnitude. So that's what it would look like, negative b there, or the opposite of b. Then again, we want to go ahead and move those tail to tip. I'm going to lose my negative sign there. That's all right. See if we can't flip that over. And then again, just using the tail to tip method here, we added tail to tip a and opposite of b, or negative b. So the resulting vector then would be the vector that gets formed from the initial point to the tip of that second vector. So there, right there, vector a minus b. Okay. All right. I believe that's going to be, oh, nope, sorry, one more slide. Here we go. We also have something called scalar products. And what they're going to do is scale the vector, basically its magnitude, and it also can affect the direction by a certain factor. So scalar k and vector v can form this vector kv, which has magnitude k, times the magnitude of v. So here's just a quick example. Draw 2u. Well, that's just basically taking vector u and doubling its magnitude. So if we go ahead and we can grab one of these vectors here, let me just clone this. Okay. And all 2u would be the same vector as u, same direction, twice as long. So this would be 2 vector u, or scalar of 2 on vector u. About twice as long is how you kind of draw them out. It doubles the force. And now these scalars can be negative as well. So if we're talking about vector negative 3u, the scalar is negative 3, and then we're going to multiply that times vector u again. Now in this case, we do need to flip the direction of the vector. The magnitude is still going to get tripled, so I'd say that's roughly 3 times longer than u. 1, 2, 3, but then it also gets to face the opposite direction in that case. So scalar products can be negative. In that case, they just still multiply the length by whatever the factor is, but then it will also switch its directions to 180 degrees in the opposite. Okay. That's the end of video 1 here, lesson 1. Go ahead and try the example problems. Thanks for watching.